definitions of a day, and Arnav would be talking about the month and year. So there is a solar day and a sidereal day. How are they different? So if I ask you how much time does it take for the Earth to rotate once about its axis, what would you say? 24 hours, 0 minutes, and 0 seconds? Well, that's not really the correct answer. The actual time period of rotation of the Earth is 23 hours, 56 minutes, and a few seconds, or roughly 4 minutes less than what our clocks call a day. Let's see why this is so. So, in astronomy, the culmination of an object is when it crosses an observer's local meridian. The local meridian is a great circle which joins the north, zenith, and south and divides the sky into two equal halves. The zenith is the point directly overhead the observer. So the local meridian is the line joining the north direction and the south direction and dividing the sky into the eastern half and the western half. So the sidereal day is the time interval between two successive culminations of a star. This is the true rotation period of the Earth because it is measured relative to the inertial frame of the background stars. So it is the time period of rotation of the Earth according to physics. But then what is the 24-hour day? This is the solar day, the time interval between two successive culminations of the sun. Let's see why it is different from the sidereal day. So the difference arises because the Earth is moving around the sun, or in the Earth's frame, the sun is moving around the Earth. And that is different from the background stars, which are stationary. So, like if you start here, let's say uh, one day, in the one day when the sun is directly overhead, uh, the star right behind it is also directly overhead. So after one sidereal day, that same star will be overhead again, but the sun will not be overhead because the Earth has moved a bit ahead, and so it will take a little more time for the sun to be overhead. And that time is proportional to the angle which the Earth has moved around the sun in one day. And that angle is around 1 degree because the Earth moves 360 degrees in 365 days. So in one day, it goes around roughly 1 degree. And the time taken by the Earth to rotate that extra 1 degree is 4 minutes. So that's why the solar day is roughly 4 minutes longer than the sidereal day. Now, let's talk about the solar day. So the solar day, the duration of the solar day is not constant throughout the year. It changes throughout the year due to several reasons, mainly due to the eccentricity of the Earth's orbit and the tilt of the Earth's equator relative to the ecliptic. So that's why we define the mean solar day. Now, the mean solar day is just the average of the solar day taken over an entire year, and that is the unit of time we use in our daily life. Now, 1/24th of the mean solar day is an hour, 1/60th of an hour is a minute, and so on. So the durations of an hour, a minute, etc., are defined relative to the mean solar day. The apparent or true solar time is given by the actual position of the sun in the sky. More precisely, it is 12 hours plus the hour angle of the sun. Now, what is the hour angle of the sun? It is the angle made by the sun from the local meridian measured about the polar axis. Now, if you've ever seen an image like this, it's a long exposure photo of the sky, which shows that all the stars in the sky appear to rotate about a fixed point in the sky, and that point is called the celestial pole. So in this diagram, the celestial pole is here, and this is the polar axis, or the axis about which the Earth is rotating, or equivalently, the stars appear to rotate. So the angle from the local meridian to the sun is the hour angle of the sun. So when the sun is on the local meridian, the hour angle is 0, and so the solar time is 12 noon. Now, the true solar time can only be measured using a sundial, not our ordinary watches. Now, the mean solar time, which our ordinary watches show, is defined relative to some object called the mean sun. This is a bit technical, but it's needed to understand the next topic, which is NLMA. So the mean sun is basically just that object whose, like, the hour angle of the true sun gives you the true solar time, right? So the hour angle of the mean sun gives you the mean solar time. The mean sun is just a fictitious object which moves along the equator at a constant angular velocity, which is equal to the mean angular velocity of the real sun in the ecliptic. So the mean solar time is defined as 12 hours plus the hour angle of the mean sun. And the difference between the mean solar time and the true solar time is called the equation of time. And it tells you basically how badly the two quantities disagree. And over an year, the equation of time varies from about minus 14 minutes to plus 16 minutes. And it's different in different days of the year. And generally, sundials have a table of values of the equation of time at various dates throughout the year so that an observer can deduce the civil time from the apparent solar time given by the sundial. And the civil time is just the mean solar time. It's called civil time because civilians use it. So that brings us to the topic of analemma. So based on whatever you heard so far, if you looked at the sun at the same time according to your wristwatch each day from the same place, would it appear at the same location in the sky? The answer is obviously no, because the sun's location in the sky at the same time of the day keeps changing throughout the year. For example, if you look at the sky at exactly 12 noon according to your watch every day, the sun won't be at the meridian every day. So the path which the sun traces over the year is called the analemma. Now, this shape arises due to the tilt of the Earth's axis and the eccentricity of its orbit around the sun. You will see the details of how exactly it arises in the module. But for now, let's see a demonstration of the analemma. Um, 1 second. Yeah. So this is a time-lapse image, time-lapse video of the same position in the sky at the same time of the day over an entire year. So as you can see, every day at 4:40 p.m., the position of the sun in the sky keeps changing. And over an entire year, it traces a distinctive path in the shape of a figure of 8, and that path is called the analemma. So this path is called the analemma. And in the bottom of the video, you might be seeing the time showing sometimes 4:40 p.m. and sometimes 5:40 p.m. That is because of daylight saving, because this video was shot in the United States. Okay, so the analemmas at different latitudes and for different times of the day always have the same overall shape, like the figure of 8 with one lobe smaller than the other that you saw in the video, but their orientations and sizes differ. Also, the analemmas have been seen from other planets as well. Like this is an analemma on Earth, and this is an analemma on Mars, clicked by the Curiosity rover. This is a link which is there in the module, which you can see to know more about the analemma. And that's all from my side. I would like to hand over to Arnav.
Yes, so I'll start with talking about the definitions of the months and years. So just like there are different definitions of the day, as Kundan talked, there are also different. So let's start with the month. So one of the first sets of months is a civil month. So this is according to whatever calendar you use. The month is given by the calendar. So that is the civil month. So that can vary from 28 days to 31 days. Next is the sidereal month. So the sidereal month is the actual revolution period of the moon around the earth. So this is roughly 27 days. But that is not what the month is there usually used, because 28 to 31, 27 does not make sense. So the month that is usually used is the synodic month. So this is the time period of one full cycle of lunar phases. So this is roughly 29.5 days, and this differs from the sidereal month because the earth is revolving around the sun. So as the earth moves along its orbit, the position of the sun changes. That's why the lunar phases take a longer time to complete compared to the sidereal month. Is a draconic month. So the moon's orbit is not in the same plane as the earth's orbit. So there are certain points along the moon's orbit where it intersects with the ecliptic. So those points are called the nodes. So there is an ascending node where the moon goes towards the north, and a descending node where the moon goes towards the south. So the time period between two ascending nodes is the draconic month. Now this also should be the same as the sidereal month. But what happens, orbit of the moon is precessing. This causes the draconic month to have a slightly different duration from the sidereal month. Now the name of the draconic month is also very interesting. So eclipses can only occur when the moon is at a node. So one ancient civilization thought that eclipses occurred because there was a dragon sitting at the nodes that would eat the sun or the moon, and that caused the eclipse. So that's how the name draconic month came. Similarly, we can talk about the definitions of the year. So the civil year is whatever the calendar year is, and that also depends on whatever calendar you use. But there are also fixed definitions of the year. So the sidereal year, this is the actual revolution period of the earth. And there is a tropical year, which is the time period for one full cycle of seasons. So there is a difference between these two, and that is because earth's orbit is also precessing, and earth's axis of rotation is also precessing. So apart from there are various other motions that the earth shows. So due to precision of earth's axis, the location of the equinox changes. This causes the change in the duration of the year. Now, there is also an anomalistic year. So, due to precision of Earth's orbit itself, the Earth's orbit is an ellipse. So, the radius of it, so the distance from the sun is changing. So, the closest point is the perihelion. So, the location of, and that causes a difference from between the anomalistic and sidereal year. So these are the various definitions of months and years. So we come to calendars. So throughout history, different civilizations have looked at the sky and looked at the regular cycles of the sun and the moon and created different calendars to keep time. So they have, based on what motions they observe, the first is the lunar calendar. So in a lunar calendar, 1 month is always the synodic month, so one full cycle of lunar phases. And they don't care about the motion of the sun. So next year is started after 12 months. So this year, the year might start in spring. A few years later, it might start in summer. They don't care. An example of this is the Islamic Hijri calendar, which is used in Arabia. And on the other end is the solar. They don't look at the phases of the moon at all. They only care about the seasons. So one solar tropical year is taken as the calendar year, and the months do not correspond to any uh, phase of the moon. Now between these two is the lunisolar calendar. So in a lunisolar calendar, they do this tight walk, tightrope walk, where the months are based on the lunar phases, but the years are supposed seasons. But there will be a misalignment. So to fix that, they use intercalary months. So some years may have 13 months instead of 12 to make up for this difference, because 12 lunar months only accounts for 354 days, while a year is 365 days. So after roughly every 2.5 years, they insert an extra month that is called the intercalary month. So let's come to specific. So the Indian lunisolar calendar is a lunisolar calendar. It was developed long, long ago in India, and many Indian festivals are still based on dates in this calendar. So in this calendar, there is something known as a tithi. So tithi is an approximation for the day. So it was observed that a synodic month is roughly 30 days. So they divided it into 30 parts, and each part called a tithi. So 360 degrees in a month, so 12 degrees in a tithi. And because moon's orbit is an ellipse, the duration of a tithi changes from 20 hours to 27 hours. So there are 30 tithis in a month and 12 months in a year. And the tithi of a given day is based on the lunar elongation at sunrise. So because the duration of a tithi may change, sometimes what happens is some tithis may get dropped altogether, or may get repeated. So this way, there is some variation in the calendar, and the month ends with a new moon day, or in some parts of the country on the full moon day, depends, but usually in the new on the new moon day. And the name of the month is based on the constellation that the moon is in on the full moon day. So there are uh, 33 constellations that the moon passes through, but there are only 12 constellations on full moon day for some reason. So what happens is, of course, this is a lunisolar calendar, so this has to have an intercalary month. So after every 32 or 33 months, an intercalary month is added. So this depends on the actual observed position of the sun. So they look at the sky, decide whether the sun has moved enough or not, and if it has, then they add a. Another old calendar is the Roman calendar. So the Roman calendar, unlike the Indian lunisolar calendar, it was not like very rigid. So the first one, what they started with, was a calendar with 10 months, March to December, and it had 304 days. Now these 304 days were in summer, spring, autumn, but there were no months in winter. So the remaining days, whatever was left, that was declared as winter, and it didn't have a month. So this system was really weird. So they couldn't keep track of time in winter. So they added 2 more months, January and February. And they decided to have a calendar of 355 days, which is of course standard for lunisolar calendar. But instead of having full months for intercalation, they what they did was every 2 years they shortened February a little and added an extra month. So this extra month with whatever the start of the year was. It could be of any duration. Whatever they felt was enough, they added it. And who decided this? It was the priests who decided this. The priests were also the astronomers, and they were supposed to look at the sky and see the moon, and based on that they were to declare that the intercalary month was ended and they were going to start a new year. Now what happened was, the priests were also politicians. So they decided in power for a year, they'll increase the length of the year. And when their opponents were in power, they'll decrease it. So this led to abuses of power, and these abuses of powers led to every province of the Roman Republic having a different New Year day. So now came Julius Caesar. So when he came to power, he discovered this and he decided that he is not going to have it. He's going to create this new year is going to be free from the interference of the priests. So he decided to call a conference of astronomers, philosophers from various parts of the republic, even from other countries like Egypt. So they decided to settle on a year of 365 days, comprising of 12 months that are January, February, March, those that we know. And every 4 years, they'll have a leap day at the end of February. So calendar. And the average length of the year was just fixed at 365.25 days, which is 11 minutes off from the correct one. So this error amounted to 1 day in 128 years. But at that time, no one lived that long, so they didn't care. So they just let it be like that. But what happened was, after many centuries, the date of the vernal equinox was shifted by 10 days. So the Pope another conference and they decided to fix it. So they decided to remove the 10 days from the calendar, first of all, to fix this. And then they decided to change the rule for leap years. Now, of course, this was done by the Pope, who is the head of the Catholic Church. So the Catholic countries of Europe adopted this immediately. But the other countries, they didn't like that the Pope said it. So they refused. But slowly, they began to understand that this was a good reform. So they adopted. Now this calendar is used everywhere. And basically, no one uses the Julian calendar. So the Gregorian calendar. So the rule for leap years is the one that we now use, where uh, years divisible by 100 that are not divisible by 400 are not leap years. So this fixed the length of the year as 365.2425 days, which is an error of 1 day in 3000 years. So now this is a really in fact, this error is more small that it is like we don't even know if the length of the year will remain constant for such a long time that this error would still be there. So nothing has been done to fix this error at all. Like there could be more complicated rules for leap years, but no one has decided to do anything. So now time is done. So let's come to coordinate systems. So the first one, that is the natural one, is the horizontal coordinate system. This coordinate system is based on how you see the sky from the ground. So you look at the sky, you measure the angle of a star from the horizon. So that will be its altitude. So that gives us one coordinate. But for a sphere, we need two coordinates. So the other one is you measure its angle from the North Pole. So that gives an azimuth. So this system is the one that like you could use on you could tell your friend right now that look at this altitude, this azimuth, there is this star. Take your telescope and see. But you couldn't do it like you're sitting in Mumbai and you tell your friend in Delhi. So that is not possible. Or you could like note down that today I saw it at this location. Tomorrow it won't be at that location. So this is not for now to like if anyone is not able to imagine this properly, you could think of it as the ground is the equatorial plane and the zenith is the north pole actually, and then altitude is the latitude and the azimuth is the longitude. So that way we can imagine. that this is how the coordinate system works. Now, of course, this horizontal coordinate system has this problem that the coordinates depend on time and location and all. So, equatorial coordinate system was created. So, there is a celestial equator now, which is the projection of Earth's equator on the celestial plane, celestial sphere. And similarly, there is a north celestial pole, a south celestial pole, which has the projection of Earth's poles. So now similarly, we can project the latitude longitude system of coordinates into the celestial sphere, and we call latitude as declination and longitude as right ascension. Now obviously we would, but what happens is right ascension is usually measured in hours, minutes and seconds, and that has an interesting thing. So what happens is if you take a right ascension of a star and add it to its hour angle, you get the hour angle of the vernal equinox. So in that way, calculating right ascension becomes easier. So that's why it's measured in hours, minutes, and seconds. So on Earth, we have the equator as 0 degree latitude, and we have prime meridian as 0 degree longitude. Sky, we can't project the prime meridian because the Earth is rotating. So instead, we take the point of the vernal equinox, the spring equinox, as the 0 degree, zero right ascension. So that allows us to create a latitude longitude system in the sky. Uh, so this is the coordinate system that is usually used for record keeping and all that. But apart from this, astronomers decided to invent more coordinate systems. One of these is the ecliptic. So now we had a latitude longitude system based on the celestial equator. So just like that, what if we had a latitude longitude system based on the ecliptic? That's what they thought. So they decided to do it. So the ecliptic latitude is just the is measured just from the ecliptic, and ecliptic longitude is measured from the vernal equinox. And just like there's a north celestial pole, a north south celestial pole, there is a north ecliptic pole, south ecliptic pole, so on. Now this is some uses. So there are various motions of the earth like precession and all that. So these have some effects on the position of the stars. It just so happens that calculating these in ecliptic coordinate system is very simple, but calculating in any other coordinate system is very difficult. You get very long formulas and all. But in this system, very easy. So that is the main use of this system. They use it to calculate these changes. And one other small use is solar systems usually lie near the plane of the ecliptic. So it becomes easier to use this coordinate system for recording their positions. So that is just the limited use of this system. Now, instead of the ecliptic, you could also have the galactic plane. So just like that, you have galactic latitude, galactic longitude, and these are measured uh, with the position with the galactic zero longitude. It just so happens that our sun is in the galactic plane, which is a lucky coincidence. So that's why this works. Otherwise, it won't. But it it happens that our sun lies in this plane, so we're able to use this system, and this can be used to record positions of objects in the galaxy for whatever reason. If you don't like the equatorial system, you can use this to do that. So these are the four main coordinate systems that astronomers use. My presentation. So if you have any doubts, you can ask.
If anyone has any doubts regarding the module or the presentation that we just had, you can say it or even just put it on the chat. We're here for a couple of more minutes.
If you have any doubts later on as well, you can message in the WhatsApp group.
Yes.
Or even DM, but asking on the WhatsApp group is better.
Okay, looks like you guys did a good job explaining everything. There is no doubt, apparently.
Either a good job or a really bad job.
I hope it's a good job. We'll find out on the assignments, I believe. Anyway, so the modules are already uploaded. Please go through them. And again, just a reminder that these sessions are not a replacement for the modules that we have provided. Please go through them for a better grasp of the subject that we just talked about. And yeah, if you have any doubts, you can always put it up on WhatsApp and Teams doubts channels, wherever, or DM anybody if you feel shy to ask publicly. But yeah, that's about it. The assignment for these sessions will also be posted soon, and the next session will also be conducted within the next couple of days. So stay tuned on the WhatsApp group and Teams. We'll just end the session here. Thanks a lot for joining.
Bye.
Bye.